Hi, I'm Tom Stephenson and welcome to Lecture 5A on Residential Construction Technology. Today we're going to be looking at roof framing, and we've got this lecture divided up into sections like usual. And so in this particular portion we're going to be looking at a cut roof, and then later on in the next section we're going to be looking at truss roof construction. So there are two distinctly different ways of framing roofs. So some of the things to identify the different components and terminology, just like when we were talking about floor framing and wall framing, we were distinguishing between headers and trimmers in a floor and lintels and jack studs in a wall. There's a lot of terminology with roofs, and it's good to get a good understanding of the terminology because you'll see it everywhere in drawings and specifications. So it's very helpful to just at least know what those terms are and how they apply to roof construction. As well, we're going to be talking about in this section cut roof, and we'll be describing how it is actually put up. And I put a link to a YouTube video that I reviewed that I think is pretty good at just giving you the fundamentals of how a common rafter is laid out. So I strongly and highly recommend that you take a look at that to bring together the whole picture of what I'm discussing, because maybe at some point you might feel a little bit fuzzy on things. And I find that if you watch a video of somebody actually cutting and constructing a roof, it can be really helpful for you to better visualize what's going on. To be honest, if I'm live in a classroom, I usually bring a couple of rafters with me and I show how it's laid up and laid out, and I hold it up on the edge of a desk and step by step go through it, and that makes it resonate with people. So I think, to be honest, I think this YouTube video will do exactly the same thing. It's really well illustrated and helpful that way. And beyond that, there's plenty of other ones that are pretty good, but I found this one particularly simple and applicable and understandable. Okay, so let's get started. And of course, we'll be talking about in the section, I'll be going over a little bit how things are described on construction drawings so that you can have the constructability aspect when you look at a set of drawings. What do I have to do to understand how this needs to be applied and managed on my project? And towards the end of the second lecture, I'll also give a little bit of a review on checklists and understanding what's happened in the framing process and how you should go about doing an inspection of the framing to make sure that things are done properly. And in the framing area, we talked about wood and expansion and contraction. Well, we want to check things as it's constructed, but also before the next stage when we start roughing in pipes and basically your plumbing, your ductwork, your electrical work, and especially also before the drywall goes on. We want to make sure that everything is where it should be, and that if we have to make some adjustments due to shrinkage, warpage, and that sort of thing, the time to do it is after the framing is complete, and to ensure that the walls are straight, etc. So we'll talk a little bit about that towards the end of the second lecture on this topic. So, as I was saying, there's two types of roofs. There's a cut roof. All a cut roof means is it's cut on site. It's not prefabricated. And so it takes more skill, to be sure. And if we went back 50 years, pretty much all roofs were cut. So, if you're doing renovation work in a house that was built in 1960, it's probably about a 95% chance that it has been a cut roof. If you look at roofs probably from about the mid-70s on, in new construction, probably a roof truss. Roof truss roofs are prefabricated and they work as part of a system of trusses. It requires less skill to install, maybe a little bit more strength to install and a little bit of extra equipment to install, but it's much quicker and it's much less costly. Although cut roofs for smaller roofs and renovations and that sort of thing, one less supplier that you have to worry about. You can get it put up. And very often in construction of new homes, the main house roof is a truss roof, but the little roofs that are on the side or at the front, they're generally cut on site. So you can have a mix match. The drawings that come with your textbook, Understanding Construction Drawings for Housing and Small Buildings, is I think, yeah, all three of them have the main roofs as truss roofs, but they also have smaller roofs like over the porch and over the box windows and a gable at the back of the Doncaster house that are actually cut on site on top of they either go on top of the truss roof or they're just separate roofs that it's easier just to cut them on site. So there's a general mix and match. So my point being, you have to know both types of roofing systems. All right, so that kind of covered that. I think the complexity of some custom homes, they may be completely cut on site, but generally the advantage too of trusses, they can span really long distances. So hard to do that with cut roofs, as you'll see. So there's a bunch of roofing terminology I have on these slides, like the span is from outside of frame wall to outside of frame wall. The rise is the vertical distance from the top of the wall to where the center lines of the roof, not the center lines, but the theoretical lines of the roof come up to a point. The run is half the span. And I'll explain this with a illustration because it's much more understandable that way. Slope is basically the relationship or the ratio between the unit rise and the unit run. And the unit run in roofing is typically going to be 12 inches. So on a drawing, it's usually going to say 412, 512, 612, 712. You might notice on your construction drawing, some of them might say 5.9912 or something like that. Why would they possibly make it 5.9912? The only reason that you'll see that on some drawings is if it's in a unionized contract. Perhaps if they go 612, they have to pay a higher rate. So they go as close as they possibly could to 6 just to stay under it, and then they don't have to pay the higher rate for framing it. The steeper the roof goes, it's a little bit more tricky to work on that particular roof. So there's extra costs and charges that may come into effect. Generally, you're not going to see that too much, but definitely in the Toronto area, it's part of union contracts, so you do see that fairly frequently. They still, if it says 5.99, you know what? They'd still frame it at 612. They just know they wouldn't get paid the extra. So unit rise and unit run, that's part of the ratio of the slope. And the theoretical line length, that's the hypotenuse of the unit rise and the unit run. So the theoretical line length or point length, if it's the unit point length, it's of the rise and the run, unit rise and run, sorry. And if it's the theoretical point length or line length, that's the length of your rafter. Then it's the hypotenuse of your your run by your total rise. So let's take a look at the pictures. I think that'll enhance this. There we go. All right. So as I was mentioning, and maybe I can just get this thing going a little bit. Just get my glasses set on this laser pointer. There we go. That's better. Okay. So we've got our span, which is from the outside of the frame building. Now, if it was a brick veneer building, it would still be to the outside of the wood frame. The brick veneer would just come to the outside because remember, the structural part of the building is on the wood frame portion. So these rafters, this is resting structurally on your studs, your stud wall. It wouldn't be resting on the brick. The brick might come up to here somewhere, but they're not going to be resting on the brick. So if that's our span, then half of the span is the run. So you just, if this was 10 feet, the span, then your run would be 5 feet as an example. And then, so this is your run, and this is your theoretical rise up to that dashed line there where it intersects this center line here. Okay, so you've got that relationship here from run to theoretical rise. Actual rise is how much the actual rafters come above that horizontal line from the top of your walls, right? So that's the actual rise. So actual rise factors in the width of the material you're using for your rafters. You could be using 2x4s, 2x6s, 2x8s, 2x10s, 2x12s, depending on the span, depending on the insulation requirements. So whatever that is will vary based on the size of materials that you're using. And our rafters actually have a little cutout where they sit on top of the plates. And we call that the bird's mouth. It kind of looks like a bird's mouth when you see it on the rafter separately. So it's got this little cutout. And the minimum building code requirement for that is 1.5 inches. So usually it's going to be more than that. Usually if your plates are 3.5 inches, you make it 3.5 inches. Or if it's 5.5 inches, you make it 5.5 inches. Although you got to be a little bit careful that you don't make it that this is compromising your rafter. So you don't want this to be too small here, right? So it depends on your overhang, depends on the rafters, but you can't have it resting less than 1.5 inches. So if you remember what we talked about with floor joists, minimum bearing for a floor joist is 1.5 inches. So the minimum bearing for a rafter is also 1.5 inches. You can have anything more than that, you can't have less than that. Okay, and so the line length, or it's also referred to as the unit length. So if you're watching some videos and somebody's calling it unit lengths, that's fine. Sorry, the unit length is over here, which is your unit slope and your unit line length, and here is your overall line length of the rafter, right? So we've got the line length, which is the hypotenuse. For those of you that are pretty good at math, the hypotenuse of your theoretical rise and your run. So that would be the length of your rafter. So if you know this and you know that, then you can always calculate this. Now, framers are not known as being the best mathematicians in the world. So you know what? They kind of worked out different ways that they can easily lay out roofs without getting too complex. And so one of the ways that they did it was they use unit rise and unit run, and they break it down into smaller components, and they use a framing square. So they use a framing square to actually calculate the roof. So, you know, if they have a unit rise of 6 inches, then that would just go from this edge here up through over here. So you'd have that would be your unit rise, and then they would take their unit run, and the unit run would be 12 inches along, and that angle is giving the slope. So that angle gives the slope. And usually you will always see on construction drawings, sort of against a roof, it'll say like 9/12, right? And that's giving you the slope. So now you know how to build the roof. So that's usually done, and I'll show you on a coming slide, and you'll see in that video how that can be laid out in practical purposes. The gentleman in the video uses a speed square. I guess I may be a little bit old school. I tend to use a framing square to lay it out, but it gets you the same result at the end of the day. And he's pretty good at showing and explaining that. All right, so we have our roof terminology down, our unit rise, our unit run, and this is really our unit line length, and the ratio between the two of them is our slope. Okay, so we're following that. We also have a overhang, and this is always something that comes under some contention too, the terminology, and sometimes I even mess it up when I say it. But the overhang is the slope line for your projection. So the roof projection is a horizontal measurement out from the wall to the outside of the rafter. Now this illustration here is not showing you all the components, and even the video here doesn't really get into some things. Like you have to allow for certain members. So for example, if this was just a house with wood siding or something on the outside, and I wanted to have a 10-inch projection, right? 10-inch projection coming out. If I wanted that to be finished 10-inch projection, I would have to lay it out so this comes out 10 inches, and then I would have to deduct for my fascia board. So if I'm putting a fascia board or what we call a rough fascia, I would have to deduct back. So if it was 1.5 inches thick, I'd have to make it 1.5 inches shorter. Almost what we have to do for the ridge board, which gets explained in the video. So we have these theoretical lines that is perfect mathematics, and then we have to deduct for the thickness of the materials that we're using. So perfect cut will bring you to the center line, then you have to deduct 3/4 horizontally on each side so that you allow for the ridge board, which goes in between, and that's what holds the rafters together as you go along. So your framing methods take this into account. And this is what we would call a common rafter. A common rafter goes from outside of wall, right, to center of ridge. So it goes from the outside of wall to the center of ridge, from the plate to the center of the ridge, and it's going at 90 degrees from the outside wall. So it's basically perpendicular to the wall. So that's coming in there. So if we take a look at this rafter and we put it into simple terms, if we have a 5/12 slope, then what we'd want to know is, well, what's the hypotenuse of 5 and 12? Because this is a right-angled triangle that we use. So this is a right-angled triangle. So if it's a right-angled triangle, then we can call on our old friend Pythagoras, and basically 5 squared plus 12 squared, and the square root of that will give us 13. So 5 squared is 25, plus 12 squared is 144, so that equals 169. Square root of 169, 13 inches. You know, you can do this in your calculator, no problem. And also, I said framers weren't that good at math, so there's what we call the framing tables here. And in the framing tables, it allows you to find some of these calculations already established and done for you. I think I have it coming up on the next slide, so I'll talk about that in a little bit more detail. So we have 5 and 12. Now, let's say that our total run was 4 feet. So that means if we had like a typical gable roof, we would have a span of 8 feet. Half the span is 4 feet, so that would give us our run. So if we actually take steps with our framing square set at 5 and 12, and we step that off 4 times, that will end up giving us our overall total line length, right? So each time, if you stepped it off and you had your framing square set at 12 and it was going up 5 inches, 12, then you do it again, 5 inches, 12, 5 inches, 12, 5 inches, 12, you will have come along 4 feet. And 4 times 13, because every time you step, you go at an angle 13. And every time you step, you go up 5 inches. So our overall length of our rafter that we would cut it at, we would run our tape measure along here, would be 52 inches. The angle that we would cut it at would be holding our framing square at 5 and 12, right? That will give us the angle to cut the rafter at, as the video will help you to visualize. So that's really how a cut roof is done. That's for a gable roof. It gets more complicated with a hip roof, but once you have and you understand how unit run, unit rise works, a good carpenter can pretty much lay out any roof from the ground. That means they don't have to go up and measure each piece. As long as you know what your span is, as long as you know what your slope is, and you know the thickness of the materials you're using, then you can calculate this and lay it out on the ground and put it up, and it will fit. Sometimes if things aren't quite square with like a hip roof, you have to do some modifications, like if the building wasn't quite square, but generally it's going to fit perfectly if the building is nice and square and level and plumb. So those things work to your advantage. That's why, going back to when we talked about foundations, it was important to try to get the foundation square, get it level, get your floors level, get your walls plumb, get them straight. Makes things a lot easier for everything as you go through the project. So if you're watching framers do the work and you see something is not straight, not plumb, not level, the sooner you get on that, the better, because it's going to transcend through the whole project that you're managing. And you're not, in this particular course, trying to become carpenters, but I think it's fundamentally important to have a good understanding of the carpentry trade and how things are laid out. And probably your mathematics level might be better than many carpenters. So you may be able to help problem solve some of the issues if you know the basic fundamentals, how roof slopes work, how point lengths work, and how you have to make compensations for thickness of materials. So it's an inevitable part of construction when you're reading construction drawings and you're having to build something, is being able to see ahead and some of the potential issues that go on that way. So yeah, so now if I was to ask you, so this, what we're saying here is that we would step this off, and the rafter unit length each time we step would be 13 inches. So that would be 52 inches from here to here, right? So that would be 52 inches from there to there. So if I was to ask you, well, what is the theoretical rise for this roof? If I was to ask you, what's the theoretical rise for this roof, what would you say? Think about it. I'll give you a minute. What's the theoretical rise for this roof? We know we stepped off 4 times 12, because that gives us 4 feet or 48 inches. All right, 4 feet is 48 inches, 12 inches times 4. We stepped this off 4 times 13. That gave us 52 inches. And if we did this calculation, we'd only have to measure the 52 inches. Now I'm saying, what's the theoretical rise for the roof? Well, we had to multiply everything by 4 steps. So you multiply this by 4. That would give you the theoretical rise for the roof, which is this, right? From there to there, the dashed line where it intersects, to the center line of the roof. Okay, so that they're all interrelated. It makes it easy to do calculations. And framers, what they would usually do is they would measure this 52 inches along the edge, mark their plumb cuts. They call those plumb cuts because they're plumb. Plumb is vertical. We don't call that level. That's plumb. This is level. Level is horizontal. Plumb is vertical. So the plumb cuts, which is this vertical cut here, that vertical cut there, it'll be, when the rafter's in place, it will be plumb, right? So from plumb cut to the building line, we call this plumb cut the building line because it's going to be in line with the edge of the frame wall, right? You would just measure 52 inches, and they would lay out their rafter and they cut their bird's mouth out, right? They would do a deduction for the thickness of the ridge over here. They'd make a template, and if they had 40 common rafters to do for this house, they'd use the template to mark all the other rafters from. They keep that one marked as a template. Because if you mark one, cut one, mark another one, cut off that one, you keep maybe going off a little bit, and by the end you could be off, you know, some of your rafters be longer or shorter. So you use one as a template, and that's the guide to mark them all from. So what they would do as a double check, they would do the step off method. So they would just step off 4 times, and if that worked out exactly to the line, they know they did everything right. Or if it's off like by an eighth or a quarter of an inch, depending how many steps, they'd probably just say, okay, that was the adjustment of the steps. The best measurement is just to lay out the 52 inches, and you're going to be right on with it. Oops. So there's the framing square that I was mentioning. I just kind of, don't worry, this doesn't go from 5 to 19 inches. Just so I could fit it in the screen, I did a little bit of CGI magic, shall we say, Star Wars magic. So at the one end of the framing square, let's see here, you've got the framing tables. All right, so at the one end you got the framing tables, and that's these over here. All right, and then let me see, something's not right here. Yeah, that's right. Framing tables are over here, and then at the other end you've got your slopes. So the number along the top, these inch numbers, that represents if you had a 212, 312, 412. So in the previous example I said a 512 roof. So that means the unit line length is 13 inches because that's the hypotenuse of 5 and 12. I always think it's important to be able to calculate where these numbers come from. So it's helpful if you actually get into framing to know how you calculate all these numbers, but they're pre-described on a framing square for a framer who doesn't want to do so much math and calculations. This goes back to the days when we didn't even have calculators. Today you could download for your phone a Construction Master calculator. I don't know what they cost now, but you download a Construction Master calculator and it does feet, inches, fractions of an inch, which is very handy because we typically don't work in decimals in framing. So that way you can easily do calculations in fractions with it, and it performs it for you. I tend to still just use a regular calculator because I don't want to forget how to do some of these things, and it's just a different choice. But framing square, very popular for those particular reasons. All right, moving on. Roof rafters and roof joists, there's not really a difference other than the slope, and the building code sort of differentiates between the slope of a roof rafter and a roof joist. So if you're greater than 3 inches, then it's considered a rafter. If you're less than 312, then it's considered a joist. And of course, if it's much lower, it's going to have heavier snow loads, and so then it's going to be deemed to be a roof joist, and the calculations are, it's almost like a flat roof then in that case, so you have to have heavier rafters to be able to support it. When you've got a steep slope roof, it's not like all the snow sits on it. A certain amount will, but that's the difference. So if you hear roof rafter or roof joist, that's the difference between the two of them. One has got a higher slope, greater than 312, and one has a lower slope. And of course, if you're using a low slope roof joist, you also have to use special shingles, because what will happen is you'll get ice formation and snow water damming, where water backs up and goes under the shingles. So they have to use a low slope shingles, which are typically a heavier shingle, and they have to have a run of basically a tar coating that's put between each layer that helps it seal between the shingles more so than regular shingles. Lost that. Okay, so this is just showing some of the components. We've got a ridge board. This is the plumb line. So that's the ridge board in the middle. There's your birds cut out. This would usually be cut this way and that way for your projection, so that you can put your fascia board and then your soffit, which goes underneath here. There would be another strap here. Forms over here. This illustration is not showing a ceiling joist. It would require a ceiling joist. It's just not showing it for simplicity's purpose. So there would be a ceiling joist. Otherwise, this would collapse the roof. It wouldn't be strong enough to hold it, unless it was a cathedral ceiling, and unless this was a ridge beam that was built up and that was going right through the structure. In those cases, then that would be different. But otherwise, this would, in the middle of the wall, it would make the walls buckle outwards. So you have a ridge board in the middle, and no ceiling joist indicated here, but it would have a ceiling joist to tie it together. And it may have a collar tie, which goes part way up. That strengthens the roof, and it requires less width on your rafters because it's more structurally sound. So there's a bunch of things that occur with that. So as I was mentioning earlier, minimum bearing 1.5 inches. Minimum bearing 1.5 inches. This looks like it's probably about 3 inches or 4 inches, depending on what this is. It looks more like a 2x4 wall. The bearing doesn't count if it's sitting on like plywood or something like the sheathing. So it's got to be bearing on the plates. Bearing on the plates. And then over here, I've got this sort of illustration. So this is showing the bearing surface here. Then you've got, so over here, this is not legal to do something like that because it's just going to split the wood once you get a load on it. We'll talk about notching and drilling when we get to the building systems and what trades sometimes do to joists and things, but this would not be legal because this would put the rafters in a vulnerable position. Your only effective width would be even less than what the height that's left on the rafter is. So bird's mouth comes out from the underneath. And here you can kind of see some framing members in place, and you can see some lookouts. They call them lookouts, where they cantilever out from the edge to support the basically your rafters that are extended out. So the lookouts will go to what they call the rake board, which is the outside member here. You can see some good terminology points here. Your fascia board that I was mentioning before is what goes on there. We call this area in here, usually we'll call it, in American textbooks, they'll usually call it the cornice. Don't ask me why they call it the cornice. We'll usually just call that our fascia soffit area, or our eaves. We tend to like to use the word eaves because the eaves trough goes out there, but the whole thing together just being referred to as the eave or the eaves comes into terminology that we use. So depending what you read and what you see, it's either going to be eaves or cornice. Here we show some knee walls that are placed in here. And if you put knee walls, then this has to be beefed up. The ceiling joist here would have to be beefed up so it doesn't deflect over here. So that's why it'd have to be, it says 25 millimeters deeper. I'm not quite sure how you get ceiling joists that are 1 inch deeper. You'd have to go up to the next size up. So if you're using 2x6s, you'd have to use 2x8s. But that's building code. This is straight from the National Building Code. And this is your rafter span is actually less. Now, students will get this confused. This is building code rafter span. There's a difference between building code rafter span and layout rafter span, right? Layout rafter span, so you can actually cut it and build it, is like from outside of plate to outside of plate. Building code rafter span is, this is the calculation I use when I figure out the span to determine what size rafters to use. So if you remember when we did our lecture on floor framing, we looked at the span and there was that one table there. And so the span is from the inside of support to inside of support. When we're doing that here, it would be just from the middle of the support to the inside of the support to the inside of the support. So we're just looking at it from there to there to there to there. And by putting the knee walls there, instead of having to have a span that would be from here to there, it greatly shortens the span, so you won't need as heavy a member. However, for building code requirements to get enough insulation in that ceiling, you might need it if it was a story and a half. In this case, it's not a livable space, but sometimes you have a story and a half, and that's livable space. So you might have a room up in here if that was the case. If you had a room up here, you'd have to have adequate insulation in your ceiling. And to get adequate insulation in your ceiling, you might have to have a much heavier rafter. Or you might have to design something with styrofoam on the inside, etc. But R value tends to drive rafter sizes sometimes more than the structural requirements. It depends on the design. So this is an example of a hip roof, hip or cottage roof. So we call it a hip or cottage roof, right? And this would be a hip roof that's around the bottom here as well. So that's a good example of this. We get combinations of, in plan view, this would be a hip roof. This would be a hip that would be going through here if it was a cut roof, so that would be a hip rafter. On an inside corner, that would be a valley. That's a valley rafter. So this is a valley rafter, that's a valley rafter, that's a valley, that's a valley. These are hips on the outside. So on an outside edge, that is your hip rafter. It's only when you've got an intersection on the inside that it is a valley rafter. So you can have all kinds of combinations, like you can have a gable roof on the end of one side, you could have a hip roof on the other, all kinds of different combinations and designs of roof to give different impacts, different effects, to serve different purposes. So that's a very common type of roof. The gable roofs and the hip rafter roofs, or the hip or cottage roofs. Very, very common types of roofs. And here's a flat roof sort of detailed drawing that was taken from the Brook drawings in your textbook, Understanding Construction Drawings. And so one of the misnomers in construction, I think that students miss on in this section, doesn't really help for that purposes, is that flat roofs aren't actually flat. they have a slope. So flat roofs will have a slope. Generally, the slope is very low slope. It's enough to make the water run to where it needs to go. So you notice in the very fine print over here, it says 2% slope towards scupper drain. Scupper drain is just a drain that's built into the roof that the water will flow to. It could be at one corner, could have one at each corner, depends on the length of the roof, could have several of them, but the roof needs to slope to that scupper drain. So if the scupper drain is somewhere over here, and then it's going to come out somewhere over here, and there'd be a downspout, then that means this part here would have to be up higher and sloping towards the scupper drain. You don't see that in the detail drawing, but they say it over here. So you got to be careful when you read drawings and you're thinking about buildability, constructability. You look at this, to me it looks flat, but you look over here, 2% slope. So somebody would be cutting tapered pieces to have the decking slope towards the drain. So that's something to consider. And we have to think about materials too. Materials deflect. That doesn't matter if you've got a steel beam. It doesn't matter if you've got a wood beam. It doesn't matter if you've got a wood joist. It doesn't matter if you've got an open web steel joist. They deflect. Now, building code requirements requires that it doesn't deflect more than 1 in 3/60ths for our purposes. So that's like 1 inch in 360 inches. But that's still deflection. So you could imagine if you build a Costco and you put all the drains at where the columns are, right? And you put that roof flat. Well, there'll be deflection in between the supports. And so that'll be the low points. Your columns that are supporting the joist wouldn't deflect because it's right on top of the footings, and the footings aren't going anywhere. We talked about undisturbed soil and basically compaction, and it's basically not moving. We've got a large footing pad that it's resting on that's spreading out the load to a bigger area. But the deflection between columns, it is. So if you have your drain right where the column is, guess what? It's going to be the high point because the other part's the low point. And so you're going to get a little pool of water that eventually is going to leak in. So things have to be designed around making sure that where your drains are going to be are not going to end up being the high points. So you have to have enough slope that that would run off, or you have to have the drain where it's going to be in the natural low point and then run the drain to the column. So there's considerations that come into play when we talk about roofs and slopes and flat roofs. Flat roofs tend to not last as long as sloping roofs, especially in low-rise residential construction. There's all kinds of different membrane materials, and then there's the tried and true hot asphalt built up roof of layers of hot asphalt and gravel that's there to absorb the heat of the sun and make it last longer. But at the end of the day, sloping roofs tend to last longer. And believe it or not, you know, up to a certain point, sloping roofs are pretty good. But if you get too steep with the sloping roofs, even that becomes a problem because wind gets underneath the shingles and blows them off. So there's happy mediums in these particular areas. And there are a lot of different roofing products and materials and assemblies that we'll talk about later on in our course and in chapter 10, I believe, when we talk about exterior finishes coming up. So these are all things, but we have to have the framing right in order to make everything else coordinate properly. And so we should be trying to get used to looking at some of these details and trying to come to some understanding, because in this case, there's the finished second floor. We have essentially, we've got a doorway or a window down below, in this case, a doorway. We've got our lintel in place here. Likely the lintel would be doubled up through here, not exactly as shown in this particular illustration. We've got our airspace between our brick veneer and our frame walls. So there's a lot of things that we have going on in this particular case. So gives you an idea of how we do cut roofs and frame them in place, and some of the processes that we need to think about. So in the next lecture, what we're going to do is we're going to get into truss roofs and some of the aspects of thinking about truss roofs. But please make sure you watch that video. I'll put the video actually in the description over here, so that you see under this YouTube video. I'll try to put a link for that video, so you can just, when you finish this, you can just maybe click on that and get a good sense of it. And if that video is not enough, just do a search on frame roofs and get a really good visualized sense of how they go together and the components and the requirements and the managerial side of it. I'll make sure I'll get through on the next video. So this is Tom Stephenson for now, wishing you a wonderful day, and we'll see you next time.